Okay, I'm back. So this is part 2 of our lectures around levelized cost of energy. Part 1 was just an overview of engineering economics, give you an idea of where this discussion is coming from. So it gives you a little background. You probably already had that, and you might have even skipped it, and I think that's fine. So so let's go ahead, and this is based on the part at the end of chapter 1 of the book. I think it's section 1.6. Encourage you to go ahead and take a look at that. Read along. So here's the question. How do you compare two very, very different sources of electricity? A coal power plant costs hundreds of millions of dollars to build. It runs 85% of the time, so it generates a lot of electricity, really big capacity. Maybe it's a 500, 600 megawatt plant. I'm sorry, it has a capacity of 1,200 megawatts. It's a big plant. Usually those are two different units creating that much energy. And it consumes coal, has a large staff when operating, so that per kilowatt hour has a fuel cost, a staff cost involved with it. Maintenance, a lot of maintenance, because these coal plants require a lot of maintenance. And how do you compare that to a single 1.5 megawatt wind turbine out on the Snake River Plain? Costs maybe $2 million to install, roughly, but absolutely no fuel, very little maintenance. Once that thing's up and running, you have to climb the tower and change the oil every year or something like that. Very minimum staff. How do you compare those two? How do you say it's so apples to oranges? And the answer lies in prorating the upfront cost, looking at that amount of present capital costs, taking into account that you usually have to finance it. You have to take out a loan and pay it back over time, so that kind of gets into the economics part. And then also look at the per kilowatt hour cost of the energy. And so we put that together in a specific formula and come up with this thing called the levelized cost of energy. Okay, and so here's how we look at it. We want to look at it on an annualized basis, breaking down to two elements, the fixed cost and the variable cost. Fixed cost we'll show later as FC. Very clever, right? FC, the fixed cost. This is incurred even if the facility created no energy in a given year. Even if it's sat idle, you still had to pay loan payments. You still had to pay some kind of maintenance, just to make sure that it didn't dry out and was ready to run. You had site security. You had some minimal staff involved. There's taxes. There's insurance. There's all these other payments. So that's the fixed cost. The variable cost is the cost incurred on a per kilowatt hour basis. So fuel is the obvious one, but generally machines, there's a maintenance schedule that's tied to how many hours it runs. So the more operation, the more maintenance. And generally, if it's running, a facility is going to require more staff. So both of those things come into play. Variable cost, fixed cost. Okay, so we want to get the fixed cost per year. And roughly speaking, the end point we're heading to is that it's the amount of capital, how much money you're going to sink into that thing to build it, times this factor called the FCR, the fixed cost recovery, or fixed charge rate. Both of those terms show up in the utilities thing. So what we want to know is what's the fixed charge rate to do it. And it generally runs between about 5% and about 20%, somewhere in that area. And it's your way of kind of prorating that big capital chunk over a period of time. Maybe it's 20 years or 30 years. And the biggest component within there is the cost of capital, that engineering economic analysis that we needed to do. So let's look at that. The utility decides to build a power plant. Well, they don't have that kind of money sitting around. They have to take out a loan. More likely, they'll sell bonds. And corporate bonds pay on the order of about 7% interest or something like that. And so what we're looking for is for a given P, given amount of this loan principal, as you will, or present value, what's that annual payment going to be required over the terms of the loan? So different different bonds might have different terms or different interest rates, but you would generally know what those are. And that A/P factor, like the one we talked about in the last lecture, is called the capital recovery factor. That's how the book calls it, capital recovery factor, CRF. And then in addition to the cost of capital, that capital recovery factor, there's the taxes and insurance and that sort of thing. So as the book describes it, you might be adding anywhere from 2 to 4%, maybe even a little bit more depending on the location and the kind of utility. So the fixed charge rate that thing we're looking for to come up with our fixed cost in a given year is equal to the capital recovery factor, the A given P factor from engineering economics, plus anywhere from 2 to 4%. So what does that look like? Very often we can look at, if we're comparing different kinds of technologies, we can look at a capital cost of a plant, not in terms of how much it costs, but how much it costs on a per kilowatt basis. So there's some sense of scale, but generally, if you're building a 300 megawatt or a 3,000 megawatt plant, it scales fairly linearly at that point. So I'm just saying, for a natural gas plant combined cycle, you might pay $1,250 per kilowatt. And of course, these are 300,000 kilowatts, 300 megawatts. So it's a lot of money, but it's a little easier if you do it on this per kilowatt basis. 1,250 is a little easier to get our head around, right? Let's say the company sells bonds to finance this at 7% or interest. It's a 25-year term. PUC allows an additional 2.5% for taxes and insurance. So what's the fixed charge rate that we apply to this to come up with that fixed cost? Well, here's the answer. You get that capital recovery factor, the A given P, 7%, 20. Look it up like we did before. That's 0.0944. We add the 2.5%. That's 0.025. Come up together. Our fixed charge rate for this example is 0.1194. Just a little shy of 12%. So we can just finish this off. The annual fixed cost for this proposed natural gas turbine is 0.1195 times 1250 per kilowatt. So it's about $149, just about $150 per kilowatt of capacity. So if it's a 300 megawatt plant, you multiply $150 by 300,000 and you get what's likely to be that annual cost that you have to deal with, that you'll have to account for in the fixed cost of that plant. Okay, variable cost. For fossil fuels, we're really talking about fuel, right? And the book does a very good job talking about it and going through it, but basically we look at the cost per energy unit of fuel. Usually for coal or natural gas, it's so many dollars per million BTUs. $6 per million BTUs is typical for natural gas. And then we have to combine that with the heat rate, the BTUs per kilowatt hour, and you end up with a number that for natural gas might be, 4 cents per kilowatt hour, okay, for fuel. Then there's operation and maintenance, usually fractions of pennies there. And then the book describes something called the levelizing factor, which allows for the possibility that fuel prices will increase over the life of the operation. Usually a good bet. 20 years from now, natural gas is likely to cost more. So just for the purpose of the example of filling this off, this natural gas plant, we'll say that the variable cost is 5 cents per kilowatt hour. So the question is, what's the cost of per kilowatt hour, taking into account both the fixed and the variable cost? Another way of looking at it, how much does the utility have to recover from the consumer just to cover the cost of building the plant and operating the plant, right? So we'll think of the levelized cost of energy, probably not what you and I pay, but what the utility is going to have to pull in to cover their base, and then probably a little bit more for their profit. So there's several different ways of looking at it. The book shows a couple different ways. I'm going to walk you through another way. But that levelized cost of energy, and that's in dollars per kilowatt hour or cents per kilowatt hour. You take that annual fixed cost, add the variable cost times the number of kilowatt hours generated, and divide by the number of kilowatts generated in that year, and you get that number we're looking for. Okay. Interesting to note that the actual size of the plant doesn't come into play. Remember, we started this discussion by saying, well, let's just say that the cost of capital, that upfront investment, is so many dollars per kilowatt of capacity. Well, once we decide to do that, then we can actually get this far down the analysis without actually saying how big is the plant. This can be very hypothetical. And it's also really valuable to think of it this way. It's very, very powerful So I'm going to recast this a little bit and say it's that annual fixed cost that we got from our fixed charge rate plus the variable cost times the number of hours it's operating in a year. So that's the capacity factor times 8760. And divide that by the number of hours it operates in a year. And so you get a slightly different equation than the book shows. That fixed cost charge, in this case it was that $149, divided by the capacity factor times 8760 plus the variable cost. Kind of a simple equation. Here's the important point, and this is what we're going to spend the next several slides on, is that the levelized cost of energy for any given facility depends on how much energy it produced. Okay, so the higher your capacity factor, the lower the levelized cost of energy. Very important point I want you to make sure you understand. And I think it's fairly straightforward to think about it. If you go to the extreme, do this thought experiment saying, well, what if I didn't make any energy from the facility that year? I still had to pay that annual cost, but I didn't have to pay any variable cost. But so you have that annual cost divided by, spread out over the whole number, all the kilowatt hours that you generated that year, which of course this time is 0. So you have fixed cost divided by 0, and you get an infinite amount. So that's the extreme to think about. Okay, so let's look at an example. We had that combined cycle natural gas plant, calculated a fixed charge rate, multiply that times my capital cost. So I end up with this $150 per kilowatt of capacity per year. My variable costs are 5 cents per kilowatt hour. So what's the levelized cost of energy? And I'm asking you to look at this for 3 different capacity factors. One at 0.2, one at 0.5, and 1.0. And I'll leave it for you to verify this. But if the capacity factor is 0.2, I get about 13 cents a kilowatt hour for my levelized cost of energy. If it's 0.5, it's 8.5 cents. And if it's 1, it's 6.7 cents. And it's important to note that 1 is the lowest. That's the lowest LCOE you'll get. And generally you won't get there because very few facilities can run full capacity 24/7 for an entire year. There's usually some kind of maintenance required. Okay. This is where it gets interesting. The book talks about this. I want to build this little graph here. And so on this horizontal axis, I've got number of hours of year. So it goes from 0 to 8,760. I tried to break that up a little bit. On this axis, I've got that fixed cost scale, that number of kilowatt hours per year. You can see I already put a little dot here at $150. Remember, it was $149. So let's see how we can put that together, how we can build that relationship between levelized cost of energy and number of hours of operation. So there's the fixed cost put there on the vertical axis. And then we draw a line which represents the variable cost. And the slope of that line, starting at the fixed cost, that slope of the line is the variable cost. It's at 5 cents per kilowatt hour. And so you see there's a lot of hours. These are really big numbers, so even 5 cents makes for a pretty steep line. Okay. And the vertical line represents our capacity factor, where we are. So I happen to draw that blue dotted line in at 0.5, right around 4,380, I think is the number of hours there. So vertical line is the capacity factor. And where that intersects is an interesting time. That shows where we are. And if we want to know what the levelized cost of energy is, we can draw a line from the origin up to that point. Okay, you follow me? It's getting busy right away, right? So here's our fixed charge. Our variable cost, VC, is the slope of that green dotted line. Pick any capacity factor. Here I picked 0.5 and draw a line from the origin to that one. And what we have, the slope of this line, which is this cost divided by these hours, is our levelized cost of energy. So remember we had what, about 3, so it looks like this point's a little right around 350 divided by 8760. What did that come up to? I'm sorry, you divide by half of 8760, which is 4380, and I get was it 4.5 cents? Pretty close to what I had before. I'm sorry, say 8 cents, which is, now I remember, was what we had for a capacity factor of 0.5. 8 cents is pretty close to what we had. 8.5 cents, it looks like, from my previous graph. And obviously this isn't a very precise graphical method. So the book shows the same graph. I just wanted to kind of give you a chance to look through and build it up one step at a time. And so this is just one kind of plant, right? That's the combined cycle natural gas plant. Some plants are more expensive, some are less expensive, some have a higher variable cost, lower variable cost. And what's fairly common in that situation is situations where if the fixed cost is higher and the variable cost is lower. So here I've got the same green line I had from our natural gas case. Let's say this blue line represents a pulverized coal plant. Higher fixed cost, but lower variable cost. So that slope is lower. And so what we see here is a point where those two lines intersect. And that's a key point here. Because if you think about it, at any given number of hours, the blue line here, below any number below around 2,800 hours, the blue line will give a more expensive energy than the green line. You want a levelized cost of energy will be lower going to the green line using the combined cycle plant for these smaller number of hours. But for longer duration operations, the blue line is cheaper because any line from the origin to any point here will have less of a slope going to the blue line than it does going to the green line. And so this trade-off between maybe less expensive high variable cost operation, and this is, for example, a gas peaker plant is like that. They're very cheap to build, but they cost a lot to run. Those are good if you only need them a few hundred hours in a year. In fact, that's what they build them for. They're called peaker plants. They're only used on those really peak days. But really expensive plants with more modest variable cost, like pulverized coal, those are good if you have them on all the time, right? You need to run them a lot of time, over time. And so this little tool, this graphical tool, are what's called screening curves. And they create the basis for some very interesting analysis. The book kind of touches on that. I actually have a whole other video because the first edition of the text has a whole chapter on this interaction. So I have another video that I'll leave as an option for you. If this is something that really floats your boat, if you're really interested in what utilities do, it's worthwhile to look at that because it gives you a little bit more insight into, for a given combination, for a given kind of load, what's the best combination of plants? What gives you the most economic plan? And of course, my final point here is that you'll see all these examples are about fossil fuel plants, which is not what the class is about. But again, understanding the business perspective of the utilities as they've come up to this point, this is what's important to understand. So I'm going to leave you at that. That's been under 20 minutes. And we'll wrap it up right now. Thanks.